So, hi everyone. Thanks so much for being here. This is the last meeting of the Philadelphia Emerging Contaminants Initiative. So, I think everyone probably knows, maybe not the people on Zoom, but this was funded by a research community seed grant from the Environmental Innovations Initiative. And so, the idea behind this community was we're going to look at water quality around Philadelphia for toxic elements, PFAS, microplastics, and really have kind of student-driven projects. So, not us saying, here's what's interesting, go study it, but you guys coming up with what's interesting. So our four student fellows, we have Tess, Pawan, Victoria, and then Prajwal, who can be here, have worked really hard on this semester. And I'm excited to see what they come up with. And so we will be able to do this again next semester, thanks to a donation from Bentley Microsystems. So we can brainstorm some project ideas and, I'd love to get your guys' feedback on what went well, what was harder than expected, how to structure it to do this project again. So I think with that, feel free to go ahead and tell us what you found out.
Hello, everyone. Thank you for the introduction, Dr. McBride. So yes, I am Victoria Valdivia. I'm a bioengineering undergrad student, and I am really fascinated by PFAS as well as social vulnerability and how that intersects with law and policy. So those are kind of my interests, and that's what brought me here to PECI. And so I'm really excited to share our results with you.
And then I'm Tess, so I'm in the Master of Urban Spatial Analytics program, and I worked for 4 years at TDS Telecom. So my job was pretty much to put microplastics and telecommunications into the ground that seeped some toxic elements as well. So I am also very interested in like the resource distribution because I would also work in rural areas. But yeah.
Hello everyone, my name is Pawan. I'm in the Masters of Environmental Studies program. Like Victoria, I'm also very interested in emerging contaminants, microplastics, PFAS in general, and how it interacted with our distribution system and drinking water system. So yeah, like excited to share about what we find.
And then Prajwal could not join us here today, but he also helped a lot with the sampling and all that stuff as well. And then as for why this matters, so actually this past January while we were sampling, there was, I believe, a watershed oil spill in Maryland that was kept secret for around 3 months by the Department of Defense. So that leads into the Piscataway, I believe. So a lot of legacy pollution from Joint Base Andrews has been a potential issue as well. And on the federal level, I think actually the administration kind of proposed the Chemical Safety and Hazard Investigation Board. They're supposed to document and be transparent about chemical incidents, and there's $0 in the budget this year, so it is a bit urgent to kind of address this. And this is one of the reasons why that we are pursuing this kind of sampling. But there are 3 emerging contaminants that we kind of focused on. So PFAS, microplastics, and toxic elements. So there's the PFAS are the synthetic chemicals, so you'll actually find them in a lot of firefighting foams, and then also food packaging, and then Apple Watches if you wear any of those. For example, and then microplastics, you will find those almost everywhere. They're pretty ubiquitous. So they can come in little fibers, or they can come in little shards or little plastic chunks. And then we have the toxic elements. So those are like lead, cadmium, arsenic, and mercury. And it's pretty it's a good focus because a lot of the water systems can be a little bit outdated. We still have pipes, for example. And all 3 of these are pretty persistent in the environment, and then they also bioaccumulate. And yeah. So we'll move on to the questions that we discussed. So a lot of drinking water begins as surface water. So I took a look at the environmental side of things. So I took samples from rivers. So I would actually go all the way upstream to Wissahickon, which is all the way up here. And then down to the Schuylkill, and then also down in Cobb's Creek, and then toward Dark, and even all the way a sample to the Delaware River to get a good gradient. Because I was really interested in the composition of urban runoff with land use. So looking at the industrial use and the residential or like residential and commercial use, with maybe a little bit more scrutiny on like the legacies of manufacturing and industry in Philadelphia. So my question was like, does the type of land like surrounding the waterway kind of indicate what kind of contaminants that it carries? And then I sampled about 14 sites, so it was a pretty good gradient that I tried to get. There were some places that were a little bit inaccessible, that I kind of had to kind of work around. But I got to Creshine, Darby, and Delaware River, Edgewood, Indian. But yeah, so it was a pretty good gradient, and I'm excited to share the results with you guys.
Sure. So the project was divided into the natural environment and the built environment, right? So for built environment, Victoria and I were interested in different stuff, but we ended up sampling the same locations. For my question, I was interested in how all of these emerging contaminants change from source to tap. So before getting on to what we found, I'd like to quickly explain the drinking water system of Philadelphia is kind of formed. So Philadelphia is highlighted in this map right here. We can full screen and also on the resumes. So Philadelphia has 3 water treatment plants. One in Baxter, one in Green Lane, and one in Belmont. And it is divided into 5 different service areas. The one in the northeast is purely served by Baxter. The small chunk that is in the southwest is served by Vermont. And the one in kind of like the northwest section is purely served by Queen Lake. The remaining 2 regions get their drinking water from a mix of these plants. For example, the one in the southwest coast region gets its drinking water from all Belmont Queen Lake and Baxter treatment plant. It's mostly Belmont. It sometimes gets it from Queen Lake and very rarely gets it from Baxter. For the one in the middle, this strip, this area gets its drinking water from Belmont and Queen Lake. So overall, this is the drinking water picture in Philadelphia. And as far as our sampling strategy goes, as I said, the Philadelphia Water Department does a lot of work before the water leaves its drinking plants, right? So it goes through settling, disinfection, coagulation, flocculation, and all the filtrations. But again, like after the water leaves the treatment plant, how does the water interact with the distribution system is what I'm kind of looking at. How does the emerging contaminants change from, in a sense, source to tap? So what we did with our sampling was we sampled about 28 sites in total. So as you can see, we have 5 in Baxter, 7 in Baxter, 6 in Queen Lake, 5 in Belmont, and 5 in the mixed areas, and another 5 in the outside mixed areas. So as I was telling before, the areas highlighted in red is served by Baxter treatment plant only. So you've like one line going to all of your sample locations, signifying that. Similarly for Queen Lake, you've got one line going to the main point, signifying it's only served by Queen Lake, and and the same for Belmont. As for the mixed served areas, like you've like water coming from all 3 regions for the yellow region, and water coming from Baxter and Queen Lake for those 2 regions. So we sampled 28 sites. if we were to distribute the site, it's 5 for Baxter, 5 for Pawan, 6 for Lake, and it's a total of 5 for all mixed. And as you can see, we've got a pretty even range, so that is something that went into when we thought about sampling. If we were to talk about the buildings that we kind of sampled, a lot of them were libraries. We had one religious center and schools, and also we had 2 community centers. So that was our sampling strategy for the built environment. To talk more about how that relates to SVI, Victoria, you can take.
Yeah, so exactly how Pawan explained with these location sites being very accessible to the community, it brings in this question of whether or not social vulnerability index or socioeconomic status is affecting the level of water contamination that we see. So we have red and blue in just like a gradient. And so blue indicates a lower social vulnerability index. So some families who are more affluent, not really seeing any economic troubles. Whereas red, the dark red here, shows the highest vulnerability. And so we wanted to see how these gradients connected to that, and to see if there's any correlation with those points. And we used libraries, community centers, religious centers, and public schools, specifically not private schools, just to ensure that we were looking at things from a community accessibility standpoint. And so wait, my question really quick is, just to say it out loud, are communities with higher social vulnerability disproportionately exposed? And also it brings this question as well, because although more impoverished families may only be able to access Dollar Tree foods and just discount stores, also the higher disposable income of a family with lower social vulnerability can allow them to be exposed to a greater amount of products. And so you have kind of at the extremes this greater level of exposure that can be theorized. And so we wanted to just not just look at the higher vulnerability status, but also to see how that relates to the lower one.
So as for what we did, I did the first kind of batch of environmental sampling around January 7th. So the temperatures were like still quite cold. But there was also, and in between batches of samples, there was January 10th, a significant rain event. It delivered like almost 1 inch of rain. That does go into account the results section. But it did mobilize a lot of the surface contaminants, and we'll get into that in the results section. And afterwards, I did some more environmental sampling to finish it off around the 12th and 14th. I generally went west first, and then I went down the northern, from Wissahickon down all the way to the Delaware on the latter halves. And then I believe the built environment was done around February and March timeline, so within the span of a month. So luckily they are not as subject to weather, inclement weather as I was. But yeah. Then for microplastics sample preparation, would you want to cover that?
Sure. So this section is kind of like what we did in the labs. So this section relates to microplastic preparation. So after we had all our samples from collected, so we brought them back to the lab. The first step that we did is we began by filtering our samples, and that again took quite a bit of time with some of the environmental samples, and surprisingly with some of the built environmental samples as well. After we filtered that, we had our microplastics in the filter paper. So we used 0.25 micrometer filter paper to do that. And after that, what we did is we put in a mixture of Fenton. So it's a kind of like a mix of iron and hydrogen peroxide to kind of incite, to kind of like make sure that the organic matters present in the filter paper would kind of dissolve away. And also what we did is we simultaneously stayed our filter papers in petri dishes with red nitrile, so we could clearly see that microplastics once we started imaging. To kind of like speed up the process and make it more efficient, we put it in a water bath for about 30 minutes at 65 degrees Celsius. And basically that brought us to the end of like preparing our samples. Now we kind of went on to analyze the samples using BioMap, the BioMap platform. So what we did was we basically brought in those samples. We had this rig where we had cameras and we placed filters in, and we had, we put the filters in and really see what was going on with the microplastics. So we tested a number of different configurations with that. So first, we kind of did the first configuration that we tested was like with no filters and at 265 nanometer wavelength. So what we had was we had a ring that would shine a light on the filter paper and be a specific wavelength to see what particles would get excited by that specific wavelength and that specific filter. So this light type is ultraviolet C. So we had that image. We had another where we did we had a yellow filter put on, and we had it at 265 nanometers. And similarly, we did a bunch of images with orange and yellow, red, and different number of wavelengths that would produce different images. At the end of that, what would happen, it would like composite it to kind of find like the number of microplastics that we would see, and also the size and also circularity. So for that we use ImageJ platform, and basically this gave us a practical way to screen for suspected microplastic in our tap water and also our garden samples, and to talk about like heavy metals into this.
Yeah, and then so I can also like provide some pictures for people. I did not put it in there, but go ahead and take a look at the microplastic photos that Pawan was talking about. Let's see. So we'll do one example. So it's like one of the filters that we can kind of zoom in on. You can kind of see like all the little, all these little critters, not critters, but like the little guys.
Use image
Yeah,
Use image 8, that's the one that we ended up using
yeah.
for image J. So those are cotton fibers, and then if you go down to the left, this little red dot here, that would be what is captured by image J, both in the size and the number that they appear in.
Yeah. Yeah, but then as for the ICP-MS, so the kind of a quick overview on this is that it was, the machine actually ionizes a sample of like arctoplasma at like thousands and thousands of degrees. And the separate resulting ions by mass to charge ratio. So the raw output is like, I think it was like counts per second, if I remember correctly. So that was like the instrument signal. And then to convert that signal to like real samples, I believe that it was comparing the corrected signal to like the reference standard. So for tap samples, we use like this specific equation or like formula, and then for like environmental samples is a little bit different. And then because like the calibration matrix, it's because the calibration matrix should match the sample matrix. So we ran like I think it was like a few batches of those, and then each with its own blank and standard, and then the calibrated batch by batch. So the final concentrations are tied to the actual instrument conditions during each run. So it's pretty much a similar logic for like the blanks, and then the calibrations for our PFAS and then the PFAS kind of pipelines. But yeah, so that was the general high level overview of the metals procedures.
Yeah, so for the PFAS sample preparation, we actually didn't do this ourselves, but this was led by Clementina Masaros with her LC-MS team. And so because PFAS can form ions, mass spectrometry becomes useful for measuring their unique mass to charge ratios and then thus determining the amount that are found in our samples. So we had a variety of samples with different volumes, both between 100 and 250 milliliters. So they were isotopically labeled with these standards. We're using 13 carbon 8 with PFOA and PFOS before that we put them into the machines. And then we used solid phase extraction with STVB to prepare it with methanol as well in order to pass it through the solid phase extraction cartridge and extract purely just the PFOS compounds. And then they were frozen. And then to create our calibration curves, we also had some standards that they created. It was 500 ml metal-free water with the different standards, and they had technical replicates to ensure that there was enough quality there. And so we used 1 milliliter of this to have the calibration and quantification. And then the PFOS compounds were eluted from the solid phase extraction cartridges using methanol, and they were dried and stored in the freezer. And then we reconstituted them with 1 ml using 96% methanol prior to putting it into the machine. And then 2 microliters of each sample was injected into the machine. So that was what we looked at. And as the PFOS compounds exit the column, they're ionized and introduced into the mass spectrometry. So if you go down, these are our different peaks that she kind of offered us, that she showed us. So each specific compound has a different peak. And then once the area ratios were reported back to us, we use standards for each PFOS to plot an area ratio versus specified amount graph to make our calibration curves. And then we would back calculate it from the calibration curve to find the percent accuracy or percent error to determine the limit of detection. And we use 15% as our guideline from the EPA, from what they recommend. So if you go down a little bit, these are our limits of detections. We had really good read for the PFOS and PFOA, which had this, the PFOS had all of the samples were above the limit of detection, and PFOA had almost all of them, and the 3 that weren't were very close. So instead of being 0.16, it was 0.154. So very close to the limit of detection. So just keep this in mind. PFNA, PFHXS, and PFBS were quite underneath the limit of detection, which could just be it's how these analyses go sometimes with the limit of detection, and it depends on the specificity and sensitivity of the machine as well. So we already knew going into it that it wasn't going to be a perfect read for everything. And so we have an asterisk on PFBS, reason being, from a regulatory standpoint with the EPA, PFBS is not evaluated by its individual concentration in nanograms, but it's included in a hazard index. And so it uses a combination of all the different PFAS to see its hazard index. And so using this equation, you would use PFBS, PFNA, PFHXS in combination with HEPA as well to be able to get the hazard index. So just reporting the concentration would not be how it's typically read in terms of its concentration and the hazard it can pose. And we use the same calibration curve to estimate the amount of PFOS in each sample using the area ratios that we already were given. And we divided them by the different sample volumes to get the exact environmental concentrations as well. So for our trials and tribulations throughout the entire process, I'm sure you guys are very interested in hearing what went wrong, what was funny, and so we're going to talk about that.
So I'll start us off. So for the first trial that we had, we started our sampling in the winter, and we kind of learned that a lot. So what we were kind of like thinking at first was we'll sample a lot of tap in parks, outdoor parks. And what we learned was that not all outdoor parks are open all year round. They generally close after mid-November in Philadelphia. So the lesson learned here is that, for the next iteration of the PECI, we should conduct our sampling outside of peak solar season and also like winter season. So basically the months of November, December, January, February, and even going as far as early to mid-March.
Yeah. And so similarly, on several occasions, the water fencing that we looked at didn't have a specific bottle filling component to it. Almost all of our samples did, which was really nice to see like the same LK filtration system. But for example, if you scroll down just a little bit, In this photo, we were at the Library of Accessible Media, which was not actually very accessible, even though it was very hard to find this library. It took us a lot of time to figure out where exactly to enter through. But it didn't have a specific bottle filling component, so we used the metal lid of the mason jar to divert the stream into the bottle. Because for the mason jar samples, we had to get 1.5 liters of them. It was 1 liter that was needed for the actual analyses, but even getting that was hard, so we had to figure out a way. And this was Prajwal and I figured this out through kind of staring at this for like 3 minutes and say, okay, we took an hour to get here. How are we gonna make this like a good use of our time? So just in the future, being able to work around these errors and just being able to, find distinct things ahead so that we're prepared for anything that comes our way. And then also, similarly, some libraries were closed unexpectedly. So even though their online website said they were open from 8 a.m. to 5 p.m. Monday through Friday, we noticed that some of our locations were just closed without notice. And this kind of was a little bit challenging for us because we had to quickly pivot and rethink our locations list, especially if this happened like 3 times for us. That means that there's 3 locations that we were counting on being able to be sampled and now are not. So we had to work around that and sit in the car for 10 more minutes and look at some more locations that fit with our research questions with both social vulnerability index and water treatment facilities that were clear to follow.
And then I'll go for my personal trial. So when I had to sample with a water sampling pole. And it was stretched out to like I think 20 feet. But on the end was like a mason jar to collect it, and that mason jar can get really heavy because it's 1 glass and it's gonna fill up with water. But I had collected several samples before this happened, and what happened is that it was slowly unscrewing, and I was not aware of it until I was sampling at Wissahickon Creek. I believe it was Wissahickon, and then it fell into the creek and very quickly sunk after many attempts trying to grab it and waiting in the water. But I also read that the Wissahickon can go several feet down, and I'm not a very strong swimmer either. So I was like, oh, okay, this may be a lost cause. So I did actually continue sampling after that. So I actually made like a little rig because I was like, oh, okay, so this is like I think it's like a 3-foot thread or something like that. I went to Home Depot, put that little thing on, and it was like an L joint. And then I got like and then I attached like a little flat bed onto it so that I could put one of the existing Nalgene bottles on it. That's a little bit smaller, a little bit more flexible, and much less heavy. So I would recommend either I know they're expensive, so either if you don't have inventory with another sampling pole, then grabbing some like DIY materials would be helpful as well. But also make sure to figure out what materials those DIY instruments are made from. So it could also like affect the sampling as well, of course. So
Yeah, for trial 5, we really wanted to use the dates, but so basically when we're thinking of source of map, we ideally want to have the data access to how the water grid is kind of laid out throughout the city, right? But we found out that those were classified information, so we could not find those data in. So we had to kind of work around that, and what we did was we ended up using the road networks themselves, because you'd imagine that the beach would run along the roads and use that as a proxy to for our grid system. So the lesson learned here would be like you always have to, as Victoria said, like be ready to pivot and be really like thinking creatively about how you can probably use another's data as a proxy, even if you don't have the data you want. And this challenge was regarding, we could not really compare our, so we sampled from February to March, but we also could not sample the source themselves, so we could not go to the drinking water plants and like sample the water in those plants. So again, we had to think on our feet and we had to sample and like, have this creative session where we like really thought about what we could do and the proxies we ended up finding for different elements was basically PWD's drinking water quality report. So we had a lot of, like, not pure numbers, but we had some statements that would, give us clues about, what concentration we'd expect to find certain chemicals. And for example, PWD's drinking water quality report said that you would not expect any arsenic or cadmium from our report. So we could probably, then interpret that as, have source water having no arsenic or cadmium. And once we find samples, like once we find arsenic and cadmium from our samples, we can then see the difference, right? And for our PFAS data, we basically had relied on UCMR 5. So this is a program under the Safe Drinking Water Act, and it's called Unregulated Contaminant Monitoring Rules. So what they do is EPA, every couple of years they come together and they look at like what contaminants should be kind of like, kind of like see in our water quality. So they make a list and they kind of tell the drinking water plants to, kind of we monitor all those contaminants. And this was the 5th iteration. They monitored over 30 contaminants as a part of this rules to potentially regulate them if it was found to be a problem. And PFAS was in this among these 30 contaminants. There are actually 5 PFAS in this UCMR. So we ended up using all of these as proxy. And the lesson learned here is, just talk with your team, just talk with your community and try to find proxies like, that can be a huge resource.
Yeah, and so again, with this classified information that comes in for these roadmaps that we have to end up using, we couldn't find an exact time for when the PWD did their official monitoring. So if our sampling periods were very different than their sampling periods, this could be potentially a little problematic, and it would introduce a little bit more distance between what is real from what is actually relevant to what we're looking at. So in the future, hopefully we can align ourselves with the EPA or PWD so that we can have an actual apples to apples full comparison between what we are seeing from the source to tap and what they're monitoring at the source as well. And then Tess, do you want to talk about that?
Yeah, so when storing samples for trace metals analysis, there were some that I had not given enough room, and then some that I had given like just enough room as well. So when they got frozen, the water expanded and it shattered like the amper valves. Yeah, so that happened. And then some of the others were like just completely fine, but obviously taking into account a little more, like, not filling up the water too far in, and then if you're freezing it, the water will expand and it'll shatter. So ideally, if you can refrigerate it, that would be best. But yeah, so another piece of inventory that was kind of broken. So
That's research.
yeah, stuff. But yeah, so that was like the lessons learned with that. Just be a little bit more cautious of the goings on that.
And one more thing really quick. So for the areas that have mixed water treatment facilities, we also want to take a look at that because PWD knows when the water is coming in, presumably, from which source. So by being able to link that back, we could have greater understanding of what water treatments, we could have more samples essentially, because we would be able to sample from 2 other service areas entirely without having to kind of guess where they're going or to treat them as big services, because it's harder to link back to a single source when we're looking at these big treatment centers.
And also to add to that, if we could also work with PWD or EPA, like to figure out the timing of when they do their, monitoring and, when they do their drinking water, monitoring for drinking water reports, and when they do their monitoring for UCMR, And we could sample ours, like, we could time our samples close to theirs, it'd be, even more relevant than.
And then, getting into the samples, so we kind of found that it was pretty ubiquitous across Philadelphia.
For the different SBI quartiles, yeah.
Yeah, so for the different SBI quartiles, but yeah, so there's not.
Quartile one, that's low.
Oh yeah, that's low to high.
So that's 0 to 0.25, which is basically the least vulnerable section. They categorize between low, medium high, and high. So this being the most vulnerable people and this being the least vulnerable individuals in Philadelphia. So it's pretty much the same throughout. And if you go down, so that's for the particle size as well.
It's still microplastics.
Yes, microplastics, yeah.
Okay. And across drinking water and natural water.
Just drinking water.
Just drinking
Because
water.
SBI comes more relevantly for what we're actually drinking out on the tap water or the filtration systems. And so when you look at particle count though, you see a little bit of difference between the median for quartile forward slightly higher than the rest. So the most vulnerable individuals in this category tend to have a higher median for the particle size for the microplastics that we found.
Yeah, and then for tributaries though, it looks like Crestline Creek was a significant outlier. However, that came after the weather, so that potentially kind of affected it, and I believe that it was like a pretty high. I think it was pretty high discharge as well. Or actually, I would need to check that, but so after the rain, so it could be like a little bit something to note right here. But then afterwards you have like the Wissahickon and Schuylkill River having a higher microplastic counts. And then like we had the right over here.
So you have 3 Schuylkill rivers on there.
Yes, so the 3 Schuylkill rivers, so it was the individual samples ranked by NP count. Yeah, so it was like so from my understanding, so each of them had like I believe that
Different sides or locations.
yeah, so these were distributed by the different times because yeah, so because I had gone back to some of the sites to not linearly like grab them. So ideally I wanted to grab them all at the same time, but because some of them were a little bit inaccessible, I had to move on down toward the down south.
So do you think those differences are a product of like temporal or spatial
It's
impacts?
yeah,
Or are they all the same size of the Schuylkill, those 3? They're
yeah.
different sizes in the Schuylkill, or they're the same?
So the sizes come into play over here. Oh, so we had like the mean count per sample and then like the mean particle area. So pretty much what I found is like, I do think that it kind of adjusts spatially, but I know that Indian Creek had like higher particles that were larger than most tributaries. So I'm wondering if it's like a source
So
of
I just
material.
poke a little bit more on that Schuylkill,
Oh, yeah.
the Schuylkill data set.
Oh,
So the variance in the Schuylkill data set between the 3 values you have there between 24 and 3 or 2 microplastic counts. Do you think that variance is a real like spatial temporal variance, or do you think that's just if you take 3 different samples at the same spot at the same time for microplastics, you're going to get 3 different numbers that span quite a wide range? That's the analytical variability or the methodological variability in the microplastic count. Because that's kind of an important thing, right? Because if you're saying at the Schuylkill River at one site, you took 3 samples at the same time, you could get 2 or you could get 23 microplastic counts. And then you're comparing all these different sites to say, well, one has 25 and one has 1. That actually might not mean anything because it might just be methodological variability in microplastic counts.
Yeah, and I would have to like drive like significant ways away, and it was like a significant time difference. So that's probably like one of the reasons for the variability is my assumption of that. But yeah, and then also I know the Schuylkill River has a significant I believe there was one guest speaker that came in to discuss like the significant variability in the Schuylkill River. So I'm wondering if it's like a similar case with this kind of with these kind of samples that I took. Yeah, so. But, let's see. So these are the other like distributions by the tributaries. So for the mean, I do want to look at the mean particle area. So aside from Indian Creek having a little bit larger particles, Wissahickon has a second highest, so they also have like a larger fragment sizes. And then there's other like smaller particles that are like more fiber types. And that's going to be, I think it was in Crescent in like Delaware, where I found where there was like more fibers. And then the mean count per sample on the left had quite a variability. And have a lot of like the particle like distributions, and then like the MP count, which is like discharge as well. It's pretty pretty surprisingly scattered. I had to go back and see in feet, cubic feet, and then like convert it to like the meters per second, or like the meters per second. So to see that if there was like any effect on like the weather conditions and things like that.
So if you compared the same site with different discharges, does a pattern emerge then?
There didn't seem to be a pattern, which I was like a little bit surprised about. Like it was like it was like a pattern that I didn't see much of it. It didn't seem like there was too much from what I saw. But yeah,
When you compare all different sites at once, it might just represent like the differences in the base flow conditions between the rivers, which is different to like whether that river's in a storm event or not.
yeah.
So there's a little bit of nuance there as well. So if you look at the same river across different discharges, that's probably a little bit more meaningful than looking at microplastic transport.
Yeah.
And, just related, I mean, they found that, your sampling is gonna change depending on where in the river you take it. So there's gonna be a lot of inherent variability in a big way. So I think just throwing that out there.
And it's just like a kind of just a heat map, seeing like on the left, like the counts versus like the sizing as well. So just like a little bit of an easier like look and see. So these are all the counts over here, and then when I over there, these are all the sizings. So it looks like the size.
This is us, right?
Yeah, so like West Philadelphia is around here. This is Cobb's area down over, or Cobb's area down over here. Yeah, so it's like quite large.
And so for PFAS, when we want to look at social vulnerability, Tess, could you just scroll down just a little more? Thank you, yeah. So it was an interesting result to see how within each quartile group of social vulnerability, again, here being the highest vulnerability, here being the lowest vulnerability, for the different PFAS, sorry, could you just like scroll a little more so we get the up for the legend? I think it's quite a large graph. Yeah, that's perfect, thank you. For PFAS, we have kind of a non-linear like behavior here, where in quartile 3 we have the highest average concentration in parts per trillion for PFAS. Similarly for PFHXS, again in the 3rd quartile, PFNA in the 3rd quartile, FOA in the 3rd quartile, and then PFBS in the 3rd quartile. And this matches some other research I did last year with blood concentrations, looking at the risk of gestational diabetes in women, looking at their PFOS concentrations. Again, like we also saw in that study, that it was the 3rd quartile that had the highest level of risk with the highest level of concentration. So it's interesting to see that PFAS as a whole kind of tend to have this non-monotonic behavior when it comes to concentrations in either blood and water as well, where this 3rd quartile area, whether it's in social vulnerability, is always going to be usually higher for all of them.
What's the EPA and it's not an action limit, but what's the recommended levels of PFAS?
Yeah, so it changes depending on which PFAS you're talking about. And also this year they're trying to actually decrease the limit, but they got involved in a lawsuit that has not been able to be enforced. So it's changed over time, but right now it's like around 4. Right?
For PFOA and PFOS, it's 4. For the rest of the three, so PA, PHXS, PF, NA, and Gen X, which is PODA. For those, that's 10 parts per trillion, and I meant to say 4 parts per trillion for PFOA and PFOS. And as Victoria mentioned, for PFBS, it's actually a combination of that, but a huge chunk of that is driven by PFBS itself, but it is a hazard index.
It takes into account the other.
It's between like it starts in 0 and theoretically could go up to infinity, but they put the regulatory compliance standard as a hazard index value of 1.
Yeah.
PFBS.
And
So for PFOS, it's 4. So there's 2 samples on there that are over. the
well,
PPA.
these are the averages for.
Oh, okay.
So if you look at the actual concentrations for every sample, I think there were quite a handful that were above this. We can talk about the locations after if you want to look at the data, the raw data we can look at. And even for PFOA as well, there were a few that were above, but the majority were below, yeah.
What's the basis for showing an average?
Just to see how each quartile is on average, because we're wanting to look at how social vulnerability is correlated with these concentrations. So there was a good amount of variability as well, some being between like 0.1 all the way to here we had, 1 to 6 parts per trillion, even one that went up to 12. So there was some variability with that. So we wanted to have an average to kind of look at that as well.
And as Victoria said, right, in the beginning, we have this 2 competing theories where, like, people probably the Q1 quartiles would, go to the dollar store and be exposed to, a lot of different products that needs to be.
And they are, if you look at just the averages, they are relatively similar. The difference is less than 0.4 parts per trillion between quartile 4 and quartile 1, which are the most drastically different social vulnerability groups. And quartile 3, like I said, is the highest for all of these on average.
Do you know how different the median concentrations would be to the mean?
I didn't think it was that different. I thought that the mean was more representative of it, but I think they were pretty similar as well when I looked at that.
Yeah, it's just generally an environmental report that we don't use averages of concentrations. Because if you're thinking about, you can say, hey, this might be an outlier, right?
Right.
So you show the range, and if you're talking about a vulnerable population, they want to know what the risk is.
Right.
If there's a hot one out there, they want to know about that.
Yeah, we can definitely
So
update this and with the median graph. I think we have one of those as well. I'd have to locate it, but it wasn't super different, so we can update that afterwards as well.
Yeah, similarly to that, like if you have a sample that's screamingly high, that's going to pull all the concentrations up, and it might just be an outlier.
Right.
So,
Yeah.
so median is usually quite accurate.
Yeah, well, we can definitely update that. Thank you. And then, this is the chart. This is the box.
Yeah, those are.
It's a little bit better.
Yeah.
So for here, for PFAS, the median is again higher than all of these. So we have this same non-monotonic behavior. If you want to scroll down to show the last one. Yeah, super high. Well, unless you say. And there actually wasn't that much variability in this one, but and they had pretty representative samples, 13, 10, 4, and 5, just because it was a little harder to find the most affluent areas with publicly accessible drinking stations as well. That was mainly seen in quartile 3 and 4 were the easiest to find these drinking stations.
Talk about PFAS in app sample. So to orient you with what's happening in the graph, we basically have a box in the whisker plot, even though it's kind of like squished in, so you really can't see here. But we've got 3 different service regions. The region that was purely served by Baxter, the region that was purely served by Belmont, that's same for Beasley. Basically, we have the overall mean shown by this line, and the crosses are basically the source concentration.
As given by the Philadelphia Water Department website.
Yes,
Yeah,
the
okay.
source concentration for PFAS was from the unmonitored contaminants monitoring group, sorry, on UCMR five, I
Right.
forget the name, but, you know, so.
Is that,
this
sorry, is that inflow water into the plant or outflow water?
That is, so they measure the water at the output before it.
Okay, before distribution.
Yes,
Okay, yeah.
after the treatment. So this is how it changes basically. So as you can see for Baxter, so Baxter basically essentially reported zero PFAS in their water. So as it goes through, you know, the distribution system, we can see some kind of uptake here. Belmont, they reported some, but it goes down for Belmont and Tweedsley. So, you know, the picture is a bit murky, so we really don't know what's
Right,
happening.
it's a change day to day, right? You don't
Yes.
know when they took those samples.
Yes,
That's interesting. They're all about the same. Yes.
yes.
I can't read the value there, or,
It's about 1 part per trillion.
Yes, so this is,
it's pretty darn good for surface water.
yes, and also this is PFBS, so this is like a hazard index. So it's a hazard, so the regulatory standard would be right here at 1, right? So it's below the regulatory standard, so we can say like, you know, overall. In terms of PFAS, PFBS specifically, I think as per our samples, the Philadelphia Water Department is doing quite good.
Thanks.
Similarly for pH excess, we have our source concentrations all at 0, so that's again UCMR. Our overall mean kinda is like at, you know, around between 0 and 2, somewhere around 1.2. And it all kind of picks up for this specific sample. And the median and the means kind of are together as well, so you know, nothing like, you know, there's not much effect of outliers, if any. And you know, if we were to talk about how safe it is in terms of like how safe the drinking water is, you can see the gap. It's pretty safe for this as well. Yeah, for PFNA, the situation is quite similar. The gap is pretty huge, and you know, we sometimes see an increase, we sometimes see a decrease, but if we could like, as you know, Samantha mentioned right now, if we can have like our samples taken in the same time window, you know, we can be more, you know, more resolute with what we convey with our findings. So PFOA, the same picture, you know, we find the same picture over and over. You see an increase, you see the decrease, but overall, it's, you know, it's quite below the legal regulatory standard. PFOS is the same picture, but it's, you know, the difference here, maybe we could do something work on PFOS. You know, it's almost, you know, it's almost quite close like to the legal standard. And I really want to mention here about Queens Lane. It seems to be for PFOS, you know, above the legal standard. But again, like the question that could arise is again with the sampling window and everything. So you know, we'd like to make our experiment design to be common results.
And just as a comment, and was evaluating a system where they were receiving water from Bucks County Water Sewer, which is from northern intake, and they were averaging around 2 on PFOA and PFOS. So you know, it's unavoidable in surface water. And New Jersey, same thing. They have some emissions there. So it's you know, yeah, like you said, it's on the edge, but it's not surprising. It's pretty funny.
And so we wanted to look at how it's related to, or sorry, correlated to SVI. And so looking at our toxic elements in red and PFOS in blue, we have a positive correlation for arsenic, PFBS, cadmium, PFNA, and then slightly for PFOA. And so we have a negative correlation with lead, copper, PFOS and PFH excess. But again, these were quite small, and I think there's a little kind of bottom, like a little. Yeah, so this specifically for the PFOS, we have SVI here in this, and in this one, or we can see here as well. And so we have the most moderate correlations, positive correlations being with PFBS, PFNA, and then very small negative correlations. And then we wanted to look at also how they correlate with one another. And PFOA correlates pretty strongly with all the other PFOS that we looked at. And then we have the other correlations which are not super strong, but specifically PFH excess and PFBS had a very strong correlation. I think that was the highest one we saw. Or sorry, PFOA and PFBS. First highest, second highest.
This is same stuff we did with toxic elements. So for arsenic, it's quite, it's below the legal standard, and so this would be the source, and this is how it changes from source to tap. So you'd kind of be looking at the mean and looking at the source, and we kind of see. But with arsenic, we can see a general increase in drinking water when it flows from source to tap, and that is something interesting. But the increase is not so much that it would trigger the regulatory limit. So the water is same in terms of arsenic.
I'd just be a little bit careful about the concentrations given by EPA stroke Philadelphia Water Department as 0, because it usually depends on the method they're using, and that their detection limits might just be much higher than what we have. So if their detection limits are like 5 micrograms per liter, they report it as 0, but actually it's still 5 micrograms. It could be like 4.5 micrograms per liter, right? So it's sometimes like when you dive into the methods that they use, they're not like legally required to report if they're below the instrument detection limit. And often that's much higher than what we can achieve in the lab here, because we don't have to abide by like EPA methods, or we don't have the same type of instrument as they have. So it's a little bit of like nuance again around how they report those concentrations, and like the devil is sometimes in the details, and sometimes those details are quite hard to find. And sometimes that's purposefully so, is that they kind of don't want to report like some of their analytical kind of like detection limits.
That's interesting.
Well, yeah, I mean, think of the consumer confidence report, they're supposed to report detection limits, even if they're saying not detect. But yeah, I would put the non-detect level and then just show that it's non-detect. And for your comparison. They need to be able to say that. It may be hidden to the obvious onlooker, but if you ask, they should be able to tell you what the detection is.
Yeah, sure. I know for a lot of the EPA methods for drinking water, the detection limit or the detection limits that are required are actually quite high.
Yeah. Because
the method is like a 25-year-old method, and it just hasn't evolved with the technology. So
It's also
I think they've come down.
Yeah. Like smaller municipalities can't afford the fancy instrumentation.
Yeah, exactly.
Sure, I mean, we can update.
Yeah, no, it's just like, it doesn't matter. It's just so just keep it in the back of mind.
For cadmium too, since we use the same detection limit, so but we can obviously change this now. But I would not say after having learned about that we see an increase, but this is what we find with the overall mean, and it's quite below what the regulatory standard is with cadmium. Copper is an interesting story though. So I think this is the only sample we kind of found was above the regulatory standard. So the way we so the way that the regulatory standard is kind of done with copper is copper and lead, both is like driven by copper and lead. So I think EPA, not the Philadelphia Water Department, does is it samples a lot of different households. I think they sampled a total of 103 households, and they put the limit at the 90th percentile of the data that they find, the concentration data that they find, and the 90th percentile would be somewhere around here, and that is what we have as our action level. And you know, it's quite above what is the EPA actions level. So here with copper, I don't know the health implications.
These are huge concentrations. These are really, really, really fine.
Right.
Yeah. For natural waters, like usually you'd find single digit microgram per liter concentrations of copper. For surface waters,
Well, what are you at there? I can't read the number.
these are thousands of
Of
micrograms.
micrograms, but that's fine. 12 is the water quality thing. And I've seen.
12 micrograms.
12 micrograms.
But these are thousands of micrograms per liter.
Right, so 1,000 would be. Is it
It's-
micrograms or
It's
No,
going
no.
to be parts per billion.
that's
Yeah.
parts per billion? I mean,
The EPA action level is what, like 1,000, 1.6.
that's for drinking, it's 1,000 for drinking water. This is 12.
This is-
Yeah.
This is
Yeah.
drinking water. All of the ones that Pawan and I have been talking about are drinking water
Yes.
from the
From these.
accessible
areas.
drinking stations.
So
Yes.
surface water, these are orders of magnitude, right?
So
The
this is
drinking water, this is still,
double the action level,
yeah.
approximately.
Yeah, because this was,
I'm pretty sure it's 12 milligrams per liter. Stop.
but I would also, just like to say that our methodology of, you know, of like giving this was not, we didn't like have a standard calibration curve, right? We just simply did the sample minus blank and by the standard. So we did not have a calibration curve. It was just like, you know, that point we we're sampling it. I mean, but that was our point where we normalize it from, but with standard methods, you want to have a calibration curve. So, you know, maybe the error could arise from our methodology as well. So, you know, we could explore further if this is actually the true scenario or not.
Oh, yeah, this is, I think this is really high. I mean, like, you know, this is,
Yeah,
Yeah, I couldn't get I worked for ages on copper and I'm forgetting numbers.
it's 1.3 milligram per liter, so this is
Yeah.
correct.
yeah, this is correct, yeah.
Yeah, so about double,
1.3 milligram per liter in drinking water.
yeah.
And I think in surface water, it's much lower.
It's supposed to be, it's like.
So this is drinking
2 orders back.
Yeah. So it's really concerning for drinking water.
Yes.
It's really, really concerning for natural waters.
Yes, but I want to like revisit our methodology before you know, just say.
Yeah, no, we should definitely revisit
Yeah, it'd
that.
be worth taking another sample.
Yeah, so the median in Pennsylvania surface waters is for the DEP is 0.084 micrograms per liter. Median.
Micrograms or milligrams?
For surface water or drinking water?
That's in surface waters, the median in Pennsylvania.
Yeah, so that's
Actually,
yeah. Yeah, that's what I would
I've
expect.
seen higher in this region.
Yeah, I would expect to see that natural, but this is drinking water as well, but this is still like,
And this was like our big find, but you know, again, like we were like kind of generally about like, you know, drawing
Right.
busted.
So we might
we
be
should have a
picking
look at
some up at the
the,
tap and the pipe and stuff. I don't know that the intake is that.
Right.
should have a look at the
but-
ICPMS data for this.
Yeah,
So, is this-
Does he have a lot of copper piping too?
Hey John, what's your
Yes.
concentration of your calibration curve? I mean, for your calibration sample?
I mean, this on the calibration curve, the highest concentration we have for copper is probably much lower than
Yeah.
these
Okay.
samples.
So I think because we extrapolated from that without the calibration curve, it could be.
It's
That
not
could be an
an issue.
issue, but it's also ICPMS methods are meant to be linearly
Oh, okay.
over 12 orders of magnitude.
Oh,
So even if you extrapolate above the calibration curve, it's going to give you a pretty roughly good estimate of what the concentration would be. It's not going to be like an order of magnitude.
Okay.
It might be like 20% out, but it's not going to be like 95% out.
And for lead, the picture is again, you know, it's pretty safe. So, but one thing I kind of like, you know, while looking at this graph, I kind of thought was like lead was a kind of very localized issue. Because, you know, you've got lead pipes released somewhere and of course they'll have lead pipes here with not in place. So, you know, the outliers here, you know, can be like driving this up. And, you know, without these like if they, I kind of like hypothesized that these were like, where the net pipes might not have been replaced. But again, we could like dig into the data.
Yeah, this is also fine. So it's also those ones in particular.
Yeah,
I
so
know the action level is like 15, but I think there's a lot of argument to bring the action level down. But
Part of that's what you were getting at earlier, which is hard to detect it,
Yeah.
right? So
yeah, you just
you
stand.
can't make the action level lower than what people
Look
can
at the
detect, yeah.
but
And that's also like the EPA have an action level, but they also quote there is no safe level of.
Right.
Right.
Yeah.
And so lastly, for SBI and our toxic elements results, we have some pretty moderate negative correlations between lead and copper and SBI, and then we have a moderate one with arsenic and somewhat moderate for cadmium. And then when you compare them with each other, seeing how they correlate, arsenic and cadmium were found to be highly correlated, as well as lead and copper, and we could say as well copper and arsenic. So these were kind of a little bit of the correlation that we saw within the cadmium metals, within the toxic elements and within SVI and toxic elements.
I wonder if that has to do with like the historical parts of the city being
Yeah.
more likely to have old pipes and also a higher wealth level.
Exactly, yeah.
Yeah, when I was actually looking at some metals data for the tributaries, like obviously you're like drawing for like a lot of like very like different things, but I know that Pacifican was a little bit higher than copper, but I do know that Pacifican, like there's some more use of algae side, and then there's like and then there's like old copper plumbing more so in this area, but also, yeah. And then I think in Manningham Canal was like higher levels of like nickel, and the Manningham Canal, nickel and chromium, the Manningham Canal has like a really old historical like history of manufacturing areas and industrial like parcels, so.
And we wanted to give a special thanks to all the organizers that helped us. It wouldn't have been possible without Derek, Samantha, Helen Kohler, John Hawkins, Clementina, who helped us with the LCMS, and we have a lot more names up here. So I mean, we really appreciate each other's work. I really appreciate Tess's work with this ArcGIS, and you guys always helping troubleshoots. And then we had some students also that we wanted to thank as well, who weren't fellows, but they were integral.
Yeah.
So thanks, thank you, Mary.
thank you.
Okay, that's all. Thank you.
Right.